All right, the purpose of this video is to go over AP Practice Problem A. In AP Practice Problem A, they give you two functions. They give you f, of which they give you the graph, and then they give you g, so don't miss this. G is an integral of f. So if you want values of g, you basically have to plug in the value here, and when you do an integral, you're getting an area. So the values of g are the areas under the curve of f, or between the curve and the x-axis. All right, so those are the two functions we've got. The questions they ask us are to find the average rate of change from -5 to 5. So that's basically the slope formula. They want us to find the instantaneous rate of change of g. So we need to take the derivative of g and find it at 3, or if it doesn't exist, state that it doesn't. They ask on what intervals is g concave up. To do concave up, we need the second derivative of g, and we need to justify our answer. And then the last part says find all x values on the interval from -5 to 5, of which g has a critical point. Remember, for g to have a critical points happen where the derivative is either 0 or undefined. So we need g's derivative, and we need to work with it. They also want us to classify the critical points. Remember, critical points can be local minimums, local maximums, or neither. And we need to justify when we find any critical points. When we tell what they are, we need to justify our answers. So let's look at how we do each one of these. Average rate of change is basically that slope formula. So to get the average rate of change, we need to take g of 5 minus g of -5 over 5 minus -5. Now you get a point for just representing this. The trouble is going further, how do I find g of 5 and g of -5? So I have the work. Basically evaluate the formula. G of 5, I'm going to plug, remember this is g of x. Wherever you see an x, you're going to plug in the x value there. So if I want g of 5, I need to plug the 5 in here. So basically I need the integral from 1 to 5 of f of t dt. That's the area under the curve from 1 to 5. So if I go to the picture from 1 to 5, here's 1, here's 5. The area between the curve and the x-axis is this section here. And to find this area, it's basically, you could use a trapezoid formula, or you could break it up into a triangle and a rectangle. So I'll just do the triangle and the rectangles. That's probably what most of you would do. So this is 2 by 4. Triangle is 1/2, 2 times 4, because it's half of that rectangle that's here. So this area should be 4, and then 2 times 4 would be this rectangle, and that would be 8. So basically this should have a total area of 12, and that's what I'm getting. Then g of -5 is a little more difficult because I'm going to integrate from 1 to -5. Now this is going the wrong way, so if you want to swap these, you could swap the limits of the integral, but you need to put a negative sign on it. So now I'm integrating the right way. I need to do negative the area from -5 to 1 of f of t dt. So explain where I'm getting this from. Let's go back to the picture. So I'm going from -5 to 1. So -5 is here. 1's here, so I need all this area down here. All this area is negative, so keep that in mind. Like when you find this triangle here, it's 3 by 4. 3 times 4 is 12, but cut in half. So this area, it's got an area 6, but we're counting it as -6. This area, this triangle, is -1. And then this is a quarter circle, so we need to find its area. Area of a circle is pi r squared. The full circle, since it has a radius of 2, if this were an entire circle, pi r squared would give us 4 pi. Since it's a quarter circle, we're going to take a quarter of 4 pi, which is just pi. But remember, it's underneath, so it's negative. So basically, I have -6 units, -1 unit, and negative pi units. Now, I accounted for those. What is this area? So leaving this negative out here, what's the area of -5 to 1? It's the -6 plus the negative pi plus the -1. This is a total of -7 minus pi. But since this negative's out here, it's going to convert this. Basically, if the inside was -7 minus pi, the negation is going to make it +7 plus positive pi. So 7 plus pi is the result. Now I can go back and get the average rate of change, because what's g of 5? Well, that was 12. What's g of negative 5? That's 7 plus pi. This bottom part comes out as 10. And just be careful that you distribute this negative. 12 minus 7 is 5, and the minus pi part, minus positive pi, will just be minus pi. So the average rate of change is 5 minus pi over 10. A little bit of a weird answer, but that's what it calculates out to be because of that circle. All right, so let's look at part B. So in part B, they're looking for the instantaneous rate of change. That's just the derivative. They want it of g at x equals 3. Well, what's the derivative of g? It's actually f of x. So remember that rule from class. If you take the derivative of an integral, so what's g prime, the derivative of the integral cancels and just throws this value in here. So this cancels, this x goes in, and since the integral is gone due to the derivative of the integral canceling, you just get f of x, and the dt also goes away. So the value of the derivative is really just f of x. Basically, it comes from that fundamental theorem of calculus that told us, the second part told us that derivatives and integrals are inverses of each other. So taking the derivative of the integral just leaves me with the original function, f of x. So g prime of x is actually f of x. So if I want g prime of 3, I really just want f of 3, and f of 3 is easy to get off the graph because it's the y value of f. Just go to 3, and the y value is 4. So there you go. Now I should be talking about the points for this. The last problem was actually 3 points. It was 1 for this expression, and then I'm not sure where the other one from the calculation came from, but basically they gave you 2 points for coming up with this calculation. All right, so that's 3 points. This is a 4th point. They only give you 1 point for this. So now part C, this part's worth 2 points. In part C, we had said that they want to know where it's concave up. So if G is going to be concave up, then G double prime has to be positive. So what is G double prime? Well, we'll use what we just found here. If G prime is f of x, G double prime needs to be f prime of x. So this needs to be true. So if G double prime of x needs to be positive, that means f prime of x needs to be positive. If f prime of x needs to be positive, let's keep in mind what f prime is. F prime represents the slopes of f. So we don't have a picture of f prime, but we can look at the slopes of f to figure out what the derivative is. So f prime of x is going to be positive where the slope of f is positive, or where f of x is increasing. Where does that happen? Well, the derivative of f is going to be positive when the function f is increasing. So there's positive slope in this interval. This is from -5 to -2. This is negative slopes. We don't want these. These are also positive slopes, and these are slopes of 0. So it's positive on this interval as well. So the two intervals are -5 to -2 and 0 to 3. And that's how I got this interval. So this is where, if you follow the logic back, this is where f is increasing. Where f is increasing is where its derivative is positive. Where its derivative is positive is where g's second derivative is positive, and that means where the original function is concave up. So the original function that we're talking about, g, is concave up on this interval. Now technically, since we're talking concavity, they put the round brackets. I'm not sure if they would take off the brackets. I don't think so, because there's only 1 point associated with this. But remember that if you're doing increase, decrease, you would close them. And then if you're doing them, you'd open them. So it's kind of, you can tell I wasn't quite sure which way to put them myself. I went with the open ones because originally I was thinking the closed ones, but then I realized it was concavity. So I think you're safer with the open ones. All right, so the points for this are basically 1 for the logic of recognizing that you need the increase of, or where, the increase of the f function to represent the derivative, represent the second derivative, so the explanation's a point, and the intervals are a point. All right, so what's left is part D. Part D wants critical points and what those critical points are. So how do we find critical points? Well, I mentioned earlier, critical points of a function are where its derivative is 0. The derivative of g of x, so g prime of x, is f of x. Remember, we did that before. So g prime of x is f of x. We just need to know where f of x is 0 to know where the critical values are. Well, where's f of x 0? Well, here's f, wherever the roots are. It's got two roots at -2 and 1. So I mentioned that f of x is 0 at these two spots, so these are the critical spots of g. Now, what are these spots? So basically, so far we've got a point. You get a point for just recognizing what it means to be a critical value. You get a point for identifying the critical values, and now you get 1 point for your justification and your labeling of each. So if you screw either one of these up, you don't get the point. Basically, I said x equals -2 is neither a max nor a min, and I'll tell you why. And x equals 1 is actually a local minimum. Now, this comes from sign changes. Basically, I need to look at what the sign does of the derivative. So what does the derivative do around -2? Well, remember, the derivative of g is f. What does f do around -2? Well, if I go up to -2, f is negative on either side. So it's negative here, hits 0, and then it's negative again. If there's no sign change for the derivative, remember, f is the derivative of g, so since f is not changing sign, g's derivative is not changing sign, so therefore this critical point is neither. Basically, the function is the original function, g, is decreasing, stops decreasing for a moment, keeps decreasing. So if you decrease, stop, decrease, you're neither a max nor a min. Now, 1, on the other hand, what's happening at 1? Well, looking at the derivative of g, which once again is f goes from negative to positive, and you can see that here. If you look at 1, it goes from being negative to positive. So if the derivative, well, remember, f's the derivative of g. If f is negative and then goes to positive, that means the original function g was decreasing, stopped, and then was increasing. If you decrease, then increase, you are a minimum. All right? So those little sign arguments, basically, they just accept if you mentioned no sign change, and here there's a sign change from negative to positive. So it justifies what these are. All right? So that's all 9 points. That's problem A. Hopefully that's helpful. Like I said, this has got a lot of good stuff in it, a lot of standard problems. It's got the max and min, it's got concavity, it's got average rate of change, and it's got an interplay between the fundamental theorem of calculus, knowing that g's derivative is f, and sort of going back and forth between those. All right? Good luck.